Good afternoon, everyone, and welcome to our webinar, Unlocking the Hidden Value of Coal Waste, Critical Minerals Recovery and Extraction. My name is Crystal Stabell, and I'm a Senior Program Coordinator with the U.S. Energy Association. To give you a few words about USAA, we're a nonprofit, apolitical, non-lobbying educational association. It represents the full gamut of the energy industry, everything from fossils to renewables to nuclear and everything in between. USAA has programs and projects all over the world. And the program we're currently under is the Consensus Program, which is a cooperative agreement with the Department of Energy's Office of Fossil Energy and Carbon Management to educate policymakers, industry, and other stakeholders to build a domestic and international consensus on the benefits of clean fossil energy and CCUS. We seek to support them through a variety of activities, such as briefings, workshops, research reports and white papers with our subcontractors, and webinars like what we're hosting today. To get back on track, we are pleased today to welcome our accomplished panelists, Dr. Rick Honaker, a professor of mining and engineering at the University of Kentucky, Dr. Marianne Alvin, a critical minerals processing senior program manager at the Department of Energy's FECM, Dr. Bridget Scanlon, research professor at the University of Texas at Austin, Bureau of Economic Geology, and finally Tem Temerbrat, a co-founder and managing partner at Nomadic Ventures. Before I begin, I have a few things that I would like to run through. First of all, this webinar is going to be recorded, and we're going to be having this available on our website. The way that the schedule is going to be working is we're going to begin with introductory remarks, giving some context and some terminology for the audience. We'll have our remarks from Dr. Honaker, Dr. Alvin, Dr. Scanlon, and Mr. Temerbrat. We'll have question times, first moderator questions, followed by audience questions. If you have any questions, you'll be able to find them down below just type them into the chat box. And for closing remarks, that will be taking place at the end. Now, I would like to be able to go through and just provide some context on what it is that's going on with the terminology. First of all, what are critical minerals? Well, critical minerals, they are a few. Forgive me, we're having a technical issue on this part. Pause for one moment, please. There we go. All right, are we able to see everything? Share screen. All right, there we go. So to begin, what are critical minerals? Critical minerals, they're non-fuel mineral resources that are essential to the economy and national security, with supply chains vulnerable to disruption. Whereas critical minerals, they're a broader range of category that includes critical minerals and other elements and materials. Rare earth elements are a group of 17 metallic elements that are critical for high-tech applications. Something to note is that rare earth elements aren't necessarily rare. They are available, they're widely dispersed. It's more of a matter of being able to access them environmentally and economically. We've got coal and their byproducts, which include fly ash, bottom ash, and coal refuse from mining and combustion, which can contain recoverable concentrations of rare earth elements and other critical materials. Acid mine drainage. This is water from abandoned coal mines that can carry dissolved rare earth elements, which can be extracted using emerging separation technologies. Finally, we've got mine tailings and overburden. Often considered waste, this can be reprocessed to extract valuable materials. So now, why is this conversation important? The United States does rely heavily on importing all of these critical minerals and rare earth elements, mostly coming from China. And this reliance right there ends up leading to an economic and a political tension right there. We're focusing on critical minerals because they enable high-tech and defense systems. We rely on these technologies for our fighter jets, for our technology, for our energy. We have economic competitiveness. When it comes to potential bottlenecks that we might experience, we want to be able to bypass that. That comes with supply chain risks as well, and being able to control this and have it produced at an economic scale. Finally, when it comes to it being foundational to energy, we use a lot of these materials and minerals when it comes to producing solar panels, to EV technology, to other and even just everyday objects, whether it be our smartphones, for example. And to be able to have a control of that is something that we consider valuable. And what we're talking about today specifically is the opportunity in coal waste and abandoned mines that we can be taking advantage of to fill this gap. So we have the untapped domestic resources. We have plenty of these minerals available in the United States. Now we just need to garner more attention towards these areas. We've got benefits projects. We've got revitalizing coal communities to be able to bring back some of this production to the United States, bring more jobs and bring more economic prosperity. And we've got it when it comes to Department of Energy's strategy. And that's what we're going to be focusing on today. We're going to be focusing on technologies and investments that are going to be needed to be able to unlock this. Now that I've gone through and given a general overview of all the terms, I'd like to turn this over to a real scientist who can tell us much more about this. So, Dr. Honecker, I would ask that you go ahead and take this away.
Thank you. Let me see. Sorry about that. I need to open my file again.
Well, you and I both had technical issues, don't worry.
I know it's not good, right? So, all right. Share. And here we go. Slideshow and begin. Can you see it? Fine.
Yes, we can.
All right, perfect. Good afternoon. My goal with this presentation is to give you a very brief snapshot at what it takes to actually unlock the critical materials from coal-based sources. And I'll start with the initial question that you have to ask when you start any project where you're extracting any critical material, any valuable element from a given primary source, and what is the mineral association? How does it associate within the feedstock that you're starting with? Rare earths in particular are associated in coal-based sources through mineral association, possibly through ion substitution in clay, which I haven't really seen a lot of, but there have been some reports, and organic association. Organic association is typically pretty high in low rank coals like lignite coals and subbituminous coals, where the humic acid concentration is pretty high. Humic acid is an excellent chelator for rare earths, and so it holds the rare earths into coal. And so in the lignites and subbituminous, you see pretty good organic association. And then as a result, you can extract the rare earth through mild acid. Most of the coals, however, are the association is through a mineral association, primarily through minerals like monazite, crandallite, xenotime, bastnasite, zircon, and apatite. So when you're considering a process for extracting these rare earths from coal-based sources, it's the ability to first being able to expose these minerals so that you can actually get to it with an acid, and then getting it in a solution so you can actually concentrate on getting the elements selectively out of solution. First, that might require some roasting under certain temperatures, which helps to convert the minerals and the associated minerals into a preferred form, so that when you subject it to a leaching process, it's perhaps more selective, eliminating as much as you can any contaminants you may have in the material that could cause a problem downstream. When you look at the rare distributions, the green line here in the graph on the left is a typical refuse source from West Kentucky 13 and Illinois Basin coal. And what's interesting is Aaron Noble at Virginia Tech actually took the USGS database and actually plotted the distributions of coals across the United States, and they pretty much all had the same kind of fingerprint, which shows that the coal sources in its pre-combustion form are high in lanthanum and cerium. It also contains a fairly decent amount of praseodymium, neodymium, samarium, even scandium, gadolinium, and dysprosium a decent amount, with minor components for the rest of the heavies. what's interesting is there's a lot of focus on acid mine drainage, and the acid mine drainage is actually coming from the same material. So the source of the AMD, acid mine drainage, is the green line. So the question is, well, why doesn't the lanthanum and cerium show up in the AMD? Why do we get a very high, heavy rare earth concentration in the AMD? Well, that's because in the source, when you're generating sulfuric acid through biological activity, oxidation of the pyrite, the calcium and sulfur forms gypsum, and gypsum, the calcium ion has the same ionic radius as lanthanum, cerium, and to some extent praseodymium. As a result, those elements get absorbed in the gypsum structure and gets deposited in the course and the refuse itself. So that's the reason why the AMD tends to have a more heavier distribution. We actually saw a lot of this in the heap leach that we actually set up. I'll show you a picture of here in a second, where we actually sort of forensically, geologically analyzed the before and after of the heap, and we found a lot of gypsum formed in the heap over a period of about 1 year of operation. So the approach that we're taking in a current project to actually extract critical materials from a coal-based source is to actually take a middling stream from an active coal plant. The reason the focus is there because previous research that we have done dating about a decade ago had shown that the middling stream actually has a pretty high elevated concentration of rare earths in their mineral matter. So we have we're focusing on that middlings material. We're crushing it, we're floating it to remove the carbon, and that carbon is going to go into graphite production. And then we're going to take the mineral matter generated from this, and we're going to go into a roasting leaching process. And then it'll go through a traditional downstream processing involving selective precipitation, solvent extraction, and variety of steps to get to high purity rare earth metals. And then in addition to that, we're going to be extracting 5 different other critical materials like manganese, cobalt, nickel, and lithium from that given source. This is a picture of a pilot plant, sort of in its sort of final stages of what we had when we wrapped up the previous project we had. We've actually taken this system apart and actually moved it from a West Kentucky site to the site here in Lexington. But this sort of shows you the leaching circuits. This actually a bioreactor tanks, 3,000 gallon bioreactor tanks with 40 horsepower motors to provide aeration and stuff. And that grew bacteria to generate sulfuric acid as a way of cost reduction. The leaching would go on here and then go into solvent extraction and several stages of selective precipitation to produce a high purity rare earth oxide. This is probably the only thing application of a heap leach in the coal industry that I've ever known. And this was actually engineered by Golden Engineers out of Colorado. It's a standard heap leach design with a clay liner, polyurethane, high density cap, and then about a few thousand tons of coal refuse put on top of it. So we analyzed this pile before we started the heap leach, and then we totally dissected it afterwards to evaluate what the changes were in the heap after 1 year of operation. We took that solution. We actually took several sources, not only the solution from this heap, but also we took coarse refuse and we put it in those leach tanks that I showed you in the picture. And then we also had a lignite source that was generated from a sand construction site, believe it or not, about 5% lignite in that sand construction material that they needed to take out anyway because nobody wants black specks in their concrete. That was lignite rich in rare earths, so we had that source and several others. You can see the high concentrations of rare earths that we were able to get it up to under various operating conditions in the plant. We also were able to take the apply a sodium sulfide precipitation to actually precipitate out all the high purity metals, nickel, cobalt being two of them, going through several stages of solvent extraction, and we were able to produce a nickel and cobalt sulfide product out of there. It was pretty high purity levels. So that sort of shows the steps. Obviously, not much time to go in detail here, but that shows the steps of how you can get from a coal source to critical materials.
Thank you for your presentation, Dr. Honecker. I would like to now welcome Dr. Alvin to give her presentation.
There we are. Slideshow from the beginning. Can everyone see the slides?
I'm afraid not. Try to click the X right there under resume slideshow.
From the beginning. Yes, there we are. Crystal, maybe you can bring it up because it's not seeming to be working for me.
Absolutely. One moment. Slideshow from the beginning.
You ready?
Yes, and here we go.
Well, thanks, Crystal, for the opportunity to present at this webinar, and also special thanks to my senior management for permitting me to do this. So what we're going to talk about are the critical minerals and materials from these unconventional resources, such as coal. And if we can go to the next slide, what I'd ask you to understand is whether it's an awesome position to be able to talk about coal by being in the Office of Fossil Energy and Carbon Management. And basically, I'm not seeing it advance, but basically what we have developed over the past number of years is the fact that we were attempting to rebuild the US leadership in being able to process and extract these materials from these unconventional materials to be able to have them for use in not only the clean energy, but also the national defense applications. From the Minerals Sustainability Division, we looked at these unconventionals, as Dr. Honecker presented, from coal prep plants, from tailings, from the overseams of the shales and the clays, to the underburdens, the materials from power generation sites, from the AMD sites, from the legacy ponds and ash ponds and so on. And currently what we're doing is expanding into not only these coal-based materials, but also into other rich materials that are rich in rare earths. We started back out in 2014. Our first funding opportunity, which Dr. Honecker was part of, looked at these materials. And what we said was that we would look at the original materials from the feed source to go through physical beneficiation, go through the hydrometallurgical circuit through extraction, separation, and refining. We looked at feasibility studies to understand how we could take these materials that had been exposed and shown in viability and proof of concept in small demonstration facilities, small pilot scale facilities, and understand whether we could take them into larger scale facilities, such as a demonstration site. So we went through some of the feed studies, the feasibility studies, and into the feed studies. We knew we could extract not only the light rare earths, but also the heavy rare earths. And we also moved into not only the rare earths, but also extracting and recovering critical minerals such as nickel, cobalt, manganese, gallium, and so on. In addition to extracting those materials, we're looking at what other value-added products can be made during the extraction process to make the processing cost-effective. We didn't target any one particular product in mind, but being able to generate these materials for multiple uses, such as in magnets, batteries, semiconductors, and so on, which would then support various sectors such as power generation, aerospace, and so on. Next slide, please. When we looked to understand, let's step back just for a moment and understand what the magnitude of our resources are. From the largest proven coal resources, we know that the US is number one. We have 250 billion of tons of reserve of coal. Russia is about 160 billion tons, China 143, followed then by Australia and India. When we think back to the year 2000, we had about 2,000 operating active coal mine sites. By 2022, we were down to about 990 active sites. Our largest producing areas in the country are in Wyoming, West Virginia, Pennsylvania, Illinois, and Kentucky. And after extracting the material, what we find is in a trade, most of the material that is being traded currently internationally is the bituminous coal, which the US supports and sends material to India, Netherlands, Japan, South Korea, and Brazil. But what makes coal so interesting versus the conventional technology is these materials not only have the light rare earths, but they also have the heavy rare earths. When we think about acid mine drainage, you're in a fluid. You don't have to beneficiate it. You don't have to grind it. So you take exception for not having the first circuit. You can easily then go into the hydrometallurgical extraction and into the separations and refining. Dr. Honecker also pointed out the association of rare earths and lignite is within the organically bound fraction, which is a lot easier to take out than some materials such as the rare earths from a glassy phase that's encapsulated in a fly ash particle. There's an abundance of rare earths in the ash resources. We have many the resources generated from power generation as well as from our legacy impoundments. And when you think about not only extracting the rare earths from these materials from the ash ponds, you're also remediating that area and reclaiming the land that these impoundments are present on. The following slide, please. Okay. When we think about the quantity of material of coal waste around the country, there's 4 billion tons scattered over about 1,000 sites. Similarly, with the legacy coal ash, there's about 2 billion tons scattered around the country at about 1,300 sites. For my colleague Evan Granite, what they did was they generated an estimate for what that would translate into the amount of material for the various critical minerals that could be available at the current rate of consumption for future use. When we look at such as neodymium and neodymium and dysprosium, we're up to 14 years of supply to 40 years of supply of these materials if we could recover these rare earths from what we already have sitting on our lands waiting for us to come and extract them. You go down to gallium and so on, and we have quite a substantially larger amount of material that could be supplied at the current rate for current use and availability. The following slide, please. When we step back in time, when we think about 2014, we had a blank sheet of paper. We issued our first funding opportunity back in 2016, and within the first 3 years, we had the first of a kind, both bench scale as well as small pilot scale facilities being generated. What you see in the top left-hand corner was the facility that Dr. Honecker talked about, where he had used his coal refuse as the material of which to extract and recover the rare earths. We had the West Virginia University facility that was extracting acid mine rare earths from acid mine drainage, as well as the fly ash system by Winter Water Surfaces and Physical Science, Inc. COVID came along, and we had a little bit of time to make sure that we had everything right and get our equipment involved. And by the year 2021-22, we had 2 additional first-of-a-kind small pilot scale facilities actually generating small quantities of material at high purity, rare earths, as well as critical minerals. We then went on and understood, well, how we take these systems and what would it take in terms of cost and effectiveness and schedule to actually build that up into a demonstration scale site that at the time we looked at 1 to 3 metric tons of mixed rare earth oxides being produced per day at a given site. The intention was to then take these feed studies and then go into these facilities shovel to ground and have them operating within the near future. Following slide, please. When we think about where we've been, we started with that clean sheet of paper. We did proof of concept testing. We understood what it would take to make these materials be our next resource of unconventional materials that would be able to be there for extraction of both rare earths and critical minerals. When we looked at the facilities that we have on hand today, we were asking those systems to only work with one type of material. When we think about the future, maybe we should think about in the sense that can those same pieces of equipment be used to actually generate materials, not only from one material, but perhaps several. Think about it in terms of the fly ash or the acid mine drainage can in that system also handle extraction and recovery from materials such as recycling of batteries and magnets. Can we add value to the cost and economics, making it more cost effective if we have other co-recovered materials in its place? We're also started looking at advanced processing to improve technology transfer and innovation in circuits and optimizing the efficiency. Could we reduce the CapEx and OpEx of the current systems that we have in functioning today? Could we interact more efficiently and effectively with our stakeholders and actually bring them into not only the construction, but also the operation, making market-ready products, new products, alloys, components, and equipment for recommending and going into process commercialization, financing, site permitting, infrastructure, and supply chains. And finally, thinking about how do we make U.S. domestic self-reliant, supporting not only the clean energy, but our national defense, commodity products, and our next generation technologies. And on the last slide, if you will, please. Or the contact information. At that point, I'll close. Thank you very much.
Thank you very much, Dr. Alvin. Next, I would like to invite Dr. Scanlon to give her presentation.
Can you see my slide?
Yes.
Okay, thank you. Thank you so much for the invitation to present here today. And it's nice to follow on from Dr. Honecker and Amira and Alvin because they provided a great background. So I'm going to talk about coal and coal ash in the Gulf Coast region. And my co-workers are Bob Reedy and Brent Elliott at the Bureau of Economic Geology. We're at the University of Texas at Austin. And Peter Warwick at the U.S. Geological Survey, and Nolan Thaker at University of North Dakota. So we were a little later to the game. We benefited from recent funding from the Department of Energy Core CM program, but also in collaborating with Nolan Thaker from North Dakota, we benefited from the work that he had been doing all along with the Department of Energy. So I'm going to try to answer the three basic questions: how much coal and coal ash is available for rare earth element extraction? What is the concentration of rare earths in coal and coal ash? And what are the trade-offs between using raw coal versus coal ash for rare earth elements? So in the Gulf Coast, the cumulative coal thickness was based on about 31,000 drill holes and other data points that Peter Warwick and Bob Reedy collated, and using kriging and GIS analysis estimated the total coal resources in the basin, which is approximately 83 billion metric tons in the upper 90 meters. Most coal in the Gulf Coast is mined using open pit mines. And so the top 90 meters is the most accessible. And Texas accounts for about 40% of the total, followed by Mississippi with 24%, Louisiana 14%, and Tennessee and Arkansas about 10% and 6% respectively. So there's a huge amount of coal resources in the basin. And this shows a map of the coal resources and the cumulative thickness up to a maximum of about 11.5 meters. So the light colors are low thickness. The reds are 0.5 to 1 meter cumulative thickness throughout the entire section. And the greens are 3 to 4 meters. And so you can see the range and the spatial variability in the coal thickness throughout the basin. And the greatest amount of data was obtained from near active or previous mines that were operating in the basin. The second, we also wanted to look at the rare earth element concentrations in the coal in the Gulf Coast. And so what we found is that the total rare earth element levels, including yttrium, on a dry coal basis, is similar to concentrations in the upper continental crust. But there were localized hotspots with up to almost 2,900 parts per million in one of the mines in Texas, in the Gibbons Creek mine. So one of the earlier speakers mentioned that rare earth elements are not truly rare. They're found in many places, but they're not oftentimes concentrated. So the fact that many of the concentrations are similar to those in the upper continental crust just confirms that. But we did find some localized hotspots. And when we looked at the ratio of the total rare earth element plus yttrium concentrations relative to the upper continental crust ratios, we find that they range from about 2 to 307 with a median of about 11. So not that much more concentrated than the upper continental crust, except for some local hotspots. So the concentration is not the only important factor in terms of rare earths, but also, as earlier speakers have mentioned, extractability is also very important. And as Rick Honecker indicated, that extractability of rare earths from lignites is very high, and work that Nolan Thieker did in our samples indicated that it was about 60 to 90% using weak acids. And this is because the rare earths are in the organic phase, and they're more readily extractable than in higher rank coals where their rare earths are in the mineral phase. And then using median price of rare earth plus yttrium plus scandium, we estimate that the value of the rare earths, considering extractability and recovery, would be about $10 per ton of coal, assuming that we could extract 50% of the rare earths from the coal. And this is the work that the North Dakota folks have done in demonstrations and bench scale studies helped us come up with some of those estimates of about 50% extraction. However, there are only 5 active mines in the Gulf Coast Basin, and they produced about 260 million tons in 2023. So most of the mines are closed at this point. And then, as Marianne mentioned, to make it economically viable, we would need to generate also co-products, and such as activated carbon or humic acids or other things. So need to look at a comprehensive assessment for economic viability. So here you can see the rare earth, the distribution of rare earth elements in coal in the samples, some of the samples that we analyzed from the Gulf Coast Basin. And so each of these is a separate sample, each bar. And you can see we're going from light to heavy, from left to right. And you can see, in some samples, lanthanum is blue and cerium is red. And so these light rare earths are fairly high in these lignite coals, and the heavy rare earths are generally lower, and there may not be much value from the light rare earth elements. And the ratio, the median ratio of light to heavy of heavy to light rare earths is about 0.4 in the data. But then you can see in the bottom then, so the top of the scale is 0 to 500 parts per million on a dry coal basis. And if you were representing that on an ash basis, it would be maybe 3 or 4 times higher, because when you burn the coal, you concentrate the rare earth elements in the ash, and so the concentrations are generally much higher. And on the bottom, then you can see this hotspot in Gibbons Creek in Texas. And here the scale is 0 to 3,000 parts per million coal. So coal ash resources in the US, this is a work that Bob Reedy did looking at all of the basins, and he estimated about 52 billion metric tons of coal produced in the US from 1950 to 2021. And then the coal ash that was generated from these power plants represents about 10% of the coal production, about 5.3 billion metric tons. And then looking at the disposition of the ash, he found that about 70% would be potentially accessible for rare earth element extraction based on Energy Information Agency data. And this is in landfills and ponds and wasn't used or sold after production. And then looking at the median rare earth element concentration data available from a paper by Taggart and others in Environmental Science and Technology. So the concentrations in the Appalachian subbituminous and bituminous coals is high, 430 milligrams per kilogram or parts per million. Illinois Basin lower, 280, and Powder River Basin lower, still 260 parts per million. And so if you consider the market value of rare earth oxides and the extractability, so the extractability is inversely related to the concentration. So the highest extractability is the Powder River Basin, where the concentrations are lowest, about 70%. And this is the work that Devine Bagdonas did in Wyoming, and lower extractability from Appalachian and Illinois coals. And so Bob Reedy estimated that the value of the rare earths based on these data is about $8.4 billion for rare earths. So then the potential in the Gulf Coast, and so we looked at the coal and we looked at the ash at the power plants, and we
Dr. Scanlon?
And what we found that the levels in coal are similar to the upper continental crust, as I explained, with localized hotspots. The median rare earth element levels in ash is about 3 times the levels in coal in the Gulf Coast. And extractability from the coal is high, 60 to 90% with weak acid, but the extractability from acid or from the ash is low because it's in a mineral phase, and as Marianne mentioned, encapsulated in silicates and stuff, and so is much lower. So then there's a trade-off then between the rare earth element concentrations in coal versus ash and extractability. So higher concentrations in ash relative to coal, but higher extractability in coal, the lignite versus the ash. And then there's the need, as Marianne also mentioned, to have other co-products to reach economic viability. And rare earth element production from ash then could offset remediation costs of ash ponds near power plants, because many of these are located adjacent to rivers and streams, and carbon co-products and societal benefits then would be required to assess socioeconomic viability. So thank you very much, and appreciate the funding of support from the Department of Energy.
Thank you, Dr. Scanlon. And finally, I would like to welcome Mr. Timurbat.
Good afternoon, everybody. I'm just going to do a single slide for you all. Let me know if you can see or have any challenges. Just send me a message here. My name is Tim. I'm the co-founder and managing partner of a firm called Nomadic Venture Partners. We are a seed stage venture capital firm investing in technologies that are looking to actually deliver the critical minerals that we need for many of the reasons that my distinguished panelists have mentioned earlier. The way we see it is we have really 3 main ways to deliver these resources. Obviously, from new mines, we need to open up several new metal mines to be able to supply the critical resources. Secondly, we need to optimize and then extract additional value from existing operations. And then thirdly, valorizing waste, just like we have been talking about here. From an investment perspective, we are a technology investor looking to invest in seed stage companies that are looking to commercialize technologies that are operating in these three core pillar areas. There are some companies that we have looked at in the space that my colleagues have mentioned here today, specifically looking at extracting rare earth elements from mine tailings, AMD, as well as coal fly ash. So these are some of the companies we have invested in so far. If you have any questions, I'm happy to answer them directly, but I will stop sharing here. And I yield my time back to Crystal.
Well, thank you very much, Tim, for your presentation, and thank you to all of our speakers. Now I'm going to go through, we have many audience questions that we're going to be getting to. So audience, if you have any more, please feel free to add them into the chat. We're looking forward to answering them. I'm going to go through and ask all of you one quick question each. And if you can keep your response to about 1 to 2 minutes, then we'll be able to get through to everyone. So Dr. Honecker, I would like to start with you. When it comes to readiness, Dr. Honecker, based on your work, where do we currently stand in terms of the technical readiness of recovering rare earth elements and other critical materials when it comes to coal refuse and byproducts?
I think the thing is that through the research that DOE's funded for over I think about a decade now, I think that many of the research groups have proven that you can extract and produce high purity critical materials from coal-based sources. The issue is the economics, and I think developing and focusing and developing new technologies or innovations or expanded knowledge into areas where we can reduce the cost of production is going to be very beneficial. The one thing that coal-based sources has a problem with is that it is a low-grade source relative to natural primary ore sources, and the fact that you can't effectively concentrate the critical materials up, prior to going into a leach tank very, very easily. And as a result, we have the challenging economics up front that we need to overcome. So things like selective lixiviants, to be able to extract the critical materials without extracting contaminants would be greatly beneficial. And other techniques downstream that would help with processing low concentrations, because it's a low concentration feedstock. Being able to process solutions, leach liquors with low concentrations of your critical materials those technologies would be beneficial. So. Yeah.
Thank you. Now I would like to turn this over to Tim. So my question for you is, how clear are the market signals for investing in coal to mineral projects today?
I think, so as an investor, we are very excited about the demand story, right? We obviously have this incredible demand story from a needs perspective, and we're constantly searching for companies that can deliver what Dr. Honecker just mentioned, right? These critical materials in an economic way. So economic viability, feasibility of these technologies, and do it at a scale is something that we think a lot about. We've looked at several different companies who are developing technologies and have gotten to that technology readiness level of 4 or 5, and often what we find is that they typically struggle to, especially in the depressed price environment that we are in currently, hard to make a very strong justification for offtake partners to partner with them at this stage. But I would say the market signals are pretty strong. Certainly, we need additional policy support to make sure that additional price depression or prolonged sort of price volatility could be de-risked and then solved. I think that's probably the bigger question, right? For many private investors looking to invest in these early stage technology companies, that can help supply really revolves around the broader market. And this is a market where it's mainly dominated by China, and because that market is opaque, many private investors are looking for policy support to be able to invest in and further develop them and hopefully rebalance that market dynamic that we have right now. But I would say that the signals are pretty strong.
Wonderful, thank you. Dr. Alvin, I'd like to turn to you. What role can Department of Energy or state energy and environmental agencies play in accelerating demonstration projects, especially in historically coal-reliant regions?
Question. Excuse me, awaiting direction from our current administration, and if permitted, continue on the path that we actually started with, in the sense that we're doing the due diligence to make sure that we assure that we de-risk anything that we would put out there in terms of an unconventional system that would be producing rare earths or critical minerals. We reinvigorate technology and innovation development and assure that where we're going into the next demonstration size, we're right sizing to maybe perhaps a larger scale than what we already have currently to show that we can actually do this. We also want greater visibility from greater visibility to our stakeholders, not only industry and government, but also the private sectors. And also there's the opportunity to have loans to be able to afford if we would actually be able to go out there and actually build a larger scale facility. So the role as we see in the future, we've got a long way to go, but we certainly have paved the way to get there.
Thank you. And now, Dr. Scanlon. When it comes to coal waste streams, such as fly ash, refuse, and acid mine drainage, they're often treated as liabilities. What are the most underappreciated opportunities these waste streams offer to critical mineral recovery? And what's standing in the way of tapping into them at scale? You're muted, Doctor.
So we have quantified the ash distribution throughout the US and what is potentially accessible. That means what hasn't been used or sold at the power plants. And electricity generation is the dominant source. So about 10% of the coal that has been burned has resulted in ash. And that ranges from about 16% ash in lignites or low rank coals to about 7 or 8% in bituminous coals and higher rank coals. And so we know that is, and 70% of the ash is accessible. The logistical issues are, what is the stage of reclamation of these ponds and landfills? If recovery of critical minerals could help offset remediation costs for regions where leaching from the ash ponds is creating contamination in groundwater or adjacent rivers. And so if the ash is being moved, maybe they could extract the critical minerals then to offset the remediation costs. So that's, there are a lot of logistical issues as each person has been talking about, but that's just some of them.
Thank you, Doctor. Now I'd like to turn to audience questions, and we've got a lot of really good questions right here. So panelists, if there's a question that you really want to answer, please feel free to just jump in and answer them as you see them. So my first one here, what are the main impediments to implementing commercial extraction of rare elements and other critical materials from coal waste and resources? Are they technical, policy, regulatory? Would anyone like to jump in?
I'll take a stab, I guess. I think the biggest impediment is really the economics. And in order for, there's so many tentacles with especially the rare earths industry, right? Because we don't actually have full control of the market on rare earths, and everybody knows this. So even the mines that produce rare earths from ores struggle with the up and down cycles of the rare earth market. And then you have the high capital costs. And there's a lot of advantages, obviously, that's already been mentioned in regards to the fact that you can take into account you can take advantage of the fact that from a coal-based source, it's already been mined. And so you don't have to incur that cost, but you have to realize that major cost item in critical material extraction is not the mine itself, it's actually the processing plant. I think if you looked at the capital and operating cost of a typical critical materials operation, it's in the processing plant that costs you more capital and more operating costs. So you have to, you have to, there's a major investment. You have to convince people who are going to provide the funding that it's going to be something that if they invest in, there's going to be a good market for it later. So I think the uncertainties and risks and permitting and all of that plays a role in defining how difficult it's going to be to open up a commercial operation involving a coal-based source because of all the risks and uncertainties about the market, and then the major capital costs that are involved in putting in an operation like that, which I think is the reason why DOE and other government agencies are trying to help out in regards to putting in maybe centralized facilities for some of this. Like, we don't need to have necessarily a rare earth purification facility at every site. We can have it centralized and then ship in from various mining operations. So there's so many different complexities and tentacles with the issues surrounding being able to make it commercial that it's hard to cover in a few minutes, but that's my point.
Well, you're doing a good job of covering it in a few minutes.
Yeah.
My next question right here. Conventional processing of rare earths is a well-known environmental trouble. How does extracting rare earths from what otherwise would be waste streams compare? Is it better, worse, or different?
I
think
think maybe I would just have a quick comment that, it just depends on the net effect. If there is a coal ash pond that's leaching contaminants into groundwater or into a nearby stream, then, if you can extract the rare earths to offset the remediation costs, and then you can move that to more a less environmentally vulnerable situation, then the net effect would be positive. So I think maybe Rick or others can, or Marianne or others could add more.
No, I think you're spot on what I was getting ready to say, and that is the acid mine drainage issue is an environmental issue already, and so that's a very easy one to address, because if they're having to treat the acid mine drainage already, which most mine sites are treating it, then the added benefit of critical material recovery is I think a welcomed, potentially economically positive venture. Because if you're it is one case where if you're already treating the acid mine drainage, you already have invested cost. And the major cost of actually extracting critical materials, that initial base solution that's needed to raise the pH to be able to treat it effectively. And if you were just starting with AMD and calculating how much caustic you would need to add in order to get to where you precipitate it out to be able to release it back into the environment, the cost of the caustic solution is more than the value of the critical materials that's in the AMD. So the fact that the mine site is already covering that cost, it benefits you greatly. When you look at the other sources, it depends. Like, just like ores, not every site and not every source is the same. So it's hard to make a universal, a description of a coal material, a refuse sample in Illinois versus one in North Dakota or whatever, because they have different leachabilities. And leachability goes a long way in defining how much environmental issue you're going to have later on, because the more acid I'm having to pour in, the more, the least, the lower the concentrations of critical materials and rare earths, the more contaminants you're going to have in the solution. And then you have to treat it. And then you have the environmental issues at the end. And I think we also have to realize that, especially on the pre-combustion side, sulfuric acid is a common acid, for example, and it dehydroxylates the clays and breaks the clays down. And when you do that, you end up releasing a lot more elements than maybe you would like. It's not selective. That's why I said before, if we had more of a selective lixiviant, we can make it a lot economically viable. It can also make it more environmentally friendly, So so not a lot of things that we can do to try to make things better than maybe even what current operations have. So yeah.
Thank you. Tim, we've got a question here for you. So what are the different policy approaches that could be used to support domestic critical mineral production, and how do investors view these different policy approaches?
Yeah, that's something that I think a lot about, because in this market where we're dealing with a country that dominates, right? I'm talking about China, dominates this market and often manipulates prices. It is really difficult for a private investor to take that risk and invest in these early stage technology companies to then, right, hopefully valorize a lot of these resources. And I think one policy idea that we often think about is, could the government provide some kind of a backstop, right, guaranteeing losses, because we don't want to have a situation where a lot of investors put up capital only to realize that it's an uneconomic and uninvestable space, right? And they wouldn't make those decisions in the first place. But if there was a sustained, prolonged, long-term policy support to step in when it's necessary, like I'm not saying, right, government should just provide handouts up front, mainly talking about in cases where, right, prices do remain depressed for a long period of time. Perhaps maybe the government can provide some funding to share the burden a little bit to keep these efforts going, so that at some point we can actually rebalance, right? So it might be, I don't know, some kind of a private insurance policy. It could be cost sharing. There could be so many different things I think that the government could do today. I do like this idea of instead of the government providing upfront capital to build the new facilities, new mines, which can be quite costly, to Dr. Honegger's point earlier, and tying up lots of capital. We're talking, several hundreds of millions of dollars per plant, right? Instead of doing that, I think that risk should be really handled by the investors, and when there is a need to actually rely on the government for potentially getting covered or reimbursed for the initial upfront cost, right? I think the government could step in and provide that when it's needed, not necessarily all the time up front. So there are so many other ideas that we can certainly get into at length, but that's one I think that could potentially incentivize private investors to partner with the government and the public to rebuild this industry.
Thank you, Tim. Our next question right here. Let's see. Is the path for recovery easier from coal mine refuse or CCR? Or would they be roughly equivalent?
So again, I said earlier that not all sources are the same. So for example, if you take a produced from a lignite source or a subbituminous source, which has a high calcium concentration, those sources typically require lower acid concentrations in order to put the critical materials in solution. So whereas if you were dealing with fly ash from pulverized coal boilers that were generated from your end product is going to be an amorphous glassy matrix of melted material that just creates it's very difficult to recover from. The amount of chemicals you have to provide are more than the value of the rares that are in them. So I think it depends on where you're at. Certainly the lignites and subbituminous ashes, and those from fluidized bed combustion, because fluidized bed combustion actually has low temperature operations that don't necessarily result in the amorphous formation, the glassy matrix. So that's an opportunity. But there are some coal-based sources, pre-combustion sources, that we talked about earlier for like the lignites and subbituminous coals that have organic associations that provide a fairly cheap stripping option, a recovery option, if you were to try to strip it away from the humic acids that Eastern coals are mostly monozites, xenotimes, and harder to get rare earths. So, yeah.
Thank you. And we have time for one last question. And let's see. Would the techniques for coal ash extraction also be appropriate for isolation of rare earth elements from incineration ash or from municipal solid waste?
I mean, if nobody wants to jump on and take the microphone away from me, I'll speak. I think in municipal solids waste, there are components within municipal solid waste that actually is fairly easy to extract critical materials from. So, but that's just like I said before, not all sources are the same, and everything has to be characterized and looked at independently of each other to identify, what is economical and what's economical and what is not economical. I'll restate the statement maybe that Dr. Scanlon said earlier, and that is, rare earths are not rare, but it's rare to find something that's economically viable to extract and purify, right? That's the rarity. And I think that we all have rares in our backyard. If you have a big farm, then you have a large resource of rares. It's just economically difficult to extract and recover. So municipal waste is a great source of future critical materials and coal-based materials, depending on where they're at, can be also. So.
Thank you, Doctor. Well, we are unfortunately out of time. Everyone asked very good questions, and I'm sorry that we couldn't get to all of them. But I would like to thank our wonderful array of panelists for giving us their time and answering all of these questions. We will have this recording available. It should be up on our website tomorrow. And if you're interested in learning more about the work that we do over on the Consensus team, or if you like this event and would like to attend future webinars, we've got several more coming up in the future, and you can subscribe on our website, which I just posted in the chat, to be able to learn more. I want to thank you all again, both the audience and our panelists, for coming out today, and I hope you all have a good day. Take care. Goodbye.